Next important distribution is binomial distribution. So let's talk about binomial distribution. The name is binom. Well, I am denoting that by a binom and with parameters, and it has two parameters, n and p. And we will say that x is a binomial distribution with that parameters n and p, and we will write in this way. So this is the notation for binomial distribution. N is natural number and p is real number between 0 and 1. P is a probability of success. We will talk about that soon. So p is a probability. So x has a binomial distribution with parameters n and p if its PMF has this form. So x is taking values 0, 1, 2, etc. up to n, this n, with these probabilities. So n choose 0 times p to the 0, 1 minus p to the n. So instead of this, I could write 1 minus p to n. Here we have n choose 1, p to the 1, 1 minus p to the n minus 1, etc. So for k, if I have k here, the probability that x will be k is the following. N choose k and times p to the k and times 1 minus p to the n minus k. And recall that we were talking about repeated trials model, and in that model we have obtained this kind of probability, exactly this binomial distribution. Soon I will give the interpretation, and that will be the same as in our previous lectures. So continuing this definition, our PMF can be written in this form. I was just writing with k, and here it is written with x. Okay. As an exercise, you can check that the sum of all these probabilities will give 1. And you will use for that the binomial formula. That's why this distribution is called binomial distribution. So let's move forward. Usage of this distribution, binomial distribution, gives the model for the repeated trials. So what we have? X is binomial with parameters n, p if the following holds. Hold. We are doing n independent repetition of some simple experiment. So we have simple experiment. We are repeating that experiment n times independently. In each simple experiment, we have some event which can happen with probability p, and if that event is happening, we are saying that we have a success, and x shows the number of successes we will have during that n trials. So how many successes we will have when doing n independent trials. Okay, so examples, we are tossing a fair coin 12 times, and we are interested in how many heads we will get during that tosses. So success is having heads. X is the number of heads we will have, number of successes we will have when doing 12 experiments, 12 trials, maybe not experiments, but trials. So in that case, x will be binom 12, 0.5. And why 0.5? This 0.5 is the probability of success. That is the probability of heads. Okay. Next. We have 5 red and 10 green balls in a box. We are drawing a ball at random, fixing its color, returning it to the box, and then doing that again 100 times. So we are repeating our experiment of taking a ball and fixing a color 100 times. we are interested in the number of green balls we will pick. So our success is picking a green ball. The probability of picking a green ball, the probability of success is, because we have 10 in 15 total, then we will have 10 over 15, which is 2 over 3. And we are doing 100 trials, then the number of green balls which we will have is binomial distributed with parameters 100 and 2 over 3. And you can give a lot of examples more. Okay, problems to solve. X is binomial distribution with parameters 20, 0.4, and Y is binomial distributed random variable with parameters 20 and 0.4. Okay, I do not know which experiment is repeated 20 times, but that's okay. I do not need that to calculate this probability. I have the complete information from this, because from this I know the PMF of X. So probability of X, the probability that X is larger than 2. Okay, first let me interpret this. So X is binomial with 20, 0.4 means X is showing the number of successes in 20 trials. So number of successes can be either 0 or 1 or 2 or etc. up to it can be 20. Every trial was a success. The probability of each success in each trial is 0.4. So here the probability of this is 20 choose 0, 0.4, 2, 0, and times, let me write it here, 1 minus 0.4 to 20 minus 0, 20. So this will give, let me erase and write that. So eraser. Okay. So this is the same as to write 0.6 to 20. So the probability that we will have 0 successes is this much. So what is the probability that we will have exactly 1 success? So this is calculated by using 20 choose 1 times 0.4 to 1 and times 0.6, 1 minus 0.4 to 19. And for 2 we will have 20 choose 2 times 0.4 squared times 0.6 to 18. And for 20 we will have 20 choose 20, which is 1, times 0.4 to 20, and times 0.6 to 0. So this is 1, this is 1, so we will have 0.4 to 20%. So this notation means that X is taking these values and with these probabilities. Now we are able to calculate this probability. So we want to calculate what is the probability that X will take all these values, one of these values. So it is much easier to calculate by using that complement formula. So this is equal to 1 minus the probability that X will be less or equal than 2. So 1 minus the probability that X will be less or equal than 2 means X can be either 0 or 1 or 2. So we need to add these 3 numbers. So we are adding them and writing here. So 0.4 to 20 plus, I will not write that 2 elements here. So plus that and plus that. Okay. So the next is calculate the probability that x is even. So probability that x is even is the same as probability that x is 0 or x is 2 or so probability that x is equal to 20. So I'm considering only even values here. So we can plug the corresponding values and calculate that. So let me write in some form. So 20 choose 2k because we are talking about only even numbers. So times 0.4 2k times 0.6 to 20 minus 2k. And k is running. If k is 0, we will have 0 here. And if k is 1, we will have 20 choose 2. This is this case, this probability case, etc. If x is 20, then 2k needs to be 20, so k is running from 0 to 10. I will not calculate the value of this sum. You can do that by using R or any other software, or you can just find a closed form formula for this by using that binomial expansion, binomial formula. Okay. The next one is calculate that y is even. But in fact, we do not have any difference between y and x. So if I will write y is even, I will have this, y is 0, y is 2, y is 20, and I will have the same probabilities. So in the sense of distributions, the probabilities will be the same. So if we have two random variables with the same distribution, and we are calculating probabilities with one of them, one of the random variables, then the same probabilities will work also for the other one. But x and y can be defined on different experiments again. Maybe we are tossing a coin or doing something and calculating x. Maybe we are rolling a die or doing something and we are calculating y. The important thing is that they have the same distribution, so everything concerning their PMF calculation of probabilities will be the same, will give the same result. Okay, another example. So 5% of population in Armenia is using VKontakte regularly. We are choosing 50 persons at random, and we are choosing with replacements. This is to have independent trials. So 50 trials. One trial is choosing one person at random because of doing with replacements model, so we can choose the same person twice or thrice. Our experiments will be independent. So what is the probability that more than 20 of them will be regular VK users? So let's denote by X the number of VK users among that 50 persons. So we are choosing 50 persons. Among that 50 persons, among that 50 trials. So in that case, we will have the following distribution. So X is the number of successes. Success in this case, so success is VK users if a person is VK user. And X will be binomial we are doing 50 trials or 50 persons we're choosing, and the probability of success is being a VK user, and the probability is 0.05. So now we know the distribution. That means we know everything to calculate probabilities concerning X. So I know the distribution, so it is X is taking the value 0 or 1 or 2, etc. up to 50 with the following probabilities. So let me write for 2, 50, choose 2 times the probability of success 0.05, 2 squared, 0.05 squared times 1 minus 0.05, 248. 50 minus 2. Okay, so we can fill this table. So we will have the PMF, and having PMF, we can calculate the probability that more than 20 of them will be a regular VK user. So let me just write the answer or that probability in the form of a sum. So we are interested that X will be larger than 20. So this is the sum of probabilities, the following probabilities. X is equal to K, and K is running from 21 to 50. And this will be, because we know this value, this will be, X is a binomial random variable with parameters 15, 0.05. So we will have 50 choose K times 0.05 to K and times 0.95 to 50 minus K. And K is running from 21 to 50. And you can calculate this sum by using R and see if this probability is large or not. In fact, this probability will be small because small chance of having almost the half of persons using VK regularly. Okay, let's move forward. So this is for binomial distribution, for plotting PMF or CDF or doing experiment and generating the random variables which are binomial distributed. Let me switch to R and do that for you. Okay, so let me erase this. So first entering, or maybe I can skip that and write in the function. So binomial name is binom. So R binom. Here I need to write how many experiments I want to do. Say I want to have one experiment. Sizes. So by the way, this is not the so again, let me recall what we are doing. This size is showing the repetition, number of repetitions of one trial. Say we are repeating something 50 times. And the probability of success is say 0.05, just like in the previous example. So what this means, this one, just once do that experiment. Doing that experiment means 50 times do that trial. Success probability is 0.5. Return us the number of successes in that one experiment of doing 50 trials. So what is doing this? Let me just run and see the result. 2. So what this means? So computer made, in some sense, made 50 trials. The success probability in each trial is 0.05, and it obtained that only 2 successes happened among these 50. Let me run that again. So I'm running that again, 3. So 3 successes when doing again 50 trials. Let me run that again, 0, no success at all. So again 3, again 3, again 5. So 5 successes when doing 50 trials with success probability 0.05 in each trial. Now let me increase this, so 10. So what is doing this? So I'm saying do that experiment of 50 trials. So do that 50 trials 10 times, and each time return me how many successes you had. So if I will run this, let me run with Control Enter, okay, or Alt Enter. So the first 50 trials resulted in 4 successes. The second 50 trials resulted in 3 successes, etc. So if I will increase the number of the probability, if I will increase the probability of success, say, do that 0.6. So probability of success is 0.6. And run this again with Alt Enter. So what this 31 means? So computer made 50 trials and found 31 successes in that 50 trials. Then it made another 50 trials with success probability in each trial 0.6, and 30 was success. And then it made another 50 trials with 39 successes, etc. So computer is doing this experiment again and again and again, and calculating the number of successes. Okay. We can plot the PMF. Okay, let me go and plot the PMF of this. So PMF was given by D binom, not R binom. R is for generating random numbers. D is for PMF or PDF, in this case PMF. Okay, so I'm doing D binom. So I will calculate the value of PMF for at the point 1, say. Size is, let me take smaller number, 20, do 20 trials. Probability is 0.6 again. So if I will calculate this is the value of PMF at 1. So probability of having exactly 1 success in 20 trials when the success of each probability, when the probability of each success is 0.6. So very low chances that we will have exactly 1 success. What about 0? The probability that we will have 0 success in that 20 trials is very small, 1 times 10 to the minus 0.8, because the probability of success is 0.6 in each trial. So if I will write what is the probability that we will have 10 successes, that is not so small as our previous probability. Okay, so I want to calculate the value of PMF, this for any number from 0 to 20. So I'm making a vector. So x is a vector running from 0 to 20. I'm running this. So I'm calculating the values of PMF at x for 0, for 1, for 2. I'm calculating all these probabilities, and I want to keep this in a variable, say y. Okay, so I'm running this. And now I want to plot that probabilities, plot xy. Type is equal to each horizontal lines, and then I will add that point. Sorry, something happened. Okay, now yeah, and now I want to add that points, at the positions XY with point character. Say, let me take 16 in this case, or maybe 17. You will see what is happening. The point character is that. Okay. Maybe I will switch to 19 and run that again. So I'm running that again. Okay, so this is our PMF. So the probability, let me zoom in. And the probability that we will have exactly 10 successes when doing 20 trials, and probability of success is 0.6, is this much, and this is 0.11 or 12, something like that. Okay, the maximum probability of success is for 12. So the maximum number of, not maximum number of successes, but the probability of having exactly k successes is the maximum when k is equal to 12. Okay, so let's move back to our slides. So next example is asking to plot in R and compare PMFs of two binomial random variables with the same number of trials but different values of P. So we will take the same values of trials, say number of trials is say 20, the same. So X is running from 0 to number of trials. Well, I need to run this and that. Now size is number of trials. I'm writing in this way, so later I will be able to change this very easily. If I will run with 10 here, then everything will be changed to 10. Okay, so this is say for 0.6, and let me call this by y1 and plot that with y1. So I'm running this. This will give the same picture because everything is the same, except you can see these are the values of y1. Now I want to add the same thing. I want to generate the PMF, but with another probability here, not the probability of success is say 0.3 or something like that. So I'm copying this, Control C, pasting here, okay, changing the name to Y2, here changing the probability, say 0.3, and let me just give another color here. So I want to plot it in the red color, and I want to have also points, my points in red color. Color is red. If I will run these three lines, okay, I forgot to change the y coordinates, so y2 for that new PMF. If I will run this, that will override this, or in fact it will open a new picture. So R is remembering, so this is previous one, etc. Okay, so R is changing the graphical screen and then doing the plot. To keep the previous one and plot on the previous graph, we can use the following. So parameter, I'm changing to parameter, new is equal to true. New is equal to true. So I'm running this. This is keeping the this graph, and now I can plot this. So I have that 2 on the same graph. In fact, this is not a correct graph, because you can see, well, x-axes are the same, but y-axes, you can see different things. The same numbers are different places. So I need to adjust the heights. To adjust that height, I need to add in this plot command, I can write the following. I can fix the range for y. So y-lim, the limits of y-lim is between, C is making vector between 0 and 0.15. And if I will give the same range for the second plot, then everything will be the same. So Control V, sorry. No, this is not working, so I'm copying this again. Control C, and then pasting here, Control V. Yeah, now I'm running this. Well, I can run from the beginning, so I'm running Control Enter, and I have this. Well, I need to take, this is not enough, let me take 25 and 25 here. So, okay, Control Enter. Now I have that picture. So you can see that red one was for 0.3 probability of success, and black one was for 0.6 probability of success. Okay, so if the success probability in one trial is 60%, 0.6, then the probability that number of successes in 20 trials will be 5, say, is small. The probability that we will have 7 successes in 20 trials is small again. But if probability of success is small, then the probability that we will have exactly 5 successes in 20 trials will be much higher, etc. So I hope this was clear. Just another trick for R. Let me do these 2 graphs not on the same graphical screen, but side by side. For doing that, we can do the following. So here, before plotting, I'm writing par, and I'm writing MF multi-frame row by rows. MF row is equal to, so I'm writing 1, 2. 1 row, 2 columns. So I'm running this, and running this. So it is doing, so it is opening, it is dividing the graphical screen into 2 parts, because I wanted to have 1 row and 2 columns, and it is putting sequentially the graphs in that screen. Okay, so let's move back. So binomial distribution example, the next example. One of our jest club has 40 seats, say, and is asking for making reservations for that seats. So historical 25% of persons who make reservations are not showing up. So the manager is a smart guy, he knows some probability, and is accepting a little bit more reservations than 40. So he's taking more reservations than the number of places. Not to have, this is for not to have many empty seats during a performance, because some persons can just not show up, go to that just club. But then there is a chance that everybody will show up, and some persons will not have a place to sit on. So our manager wants to limit this risk, the probability of having more than 40 persons, to 5%. So he wants to have that the probability that someone will be standing less than 5%. So what is the maximum number of reservations that he can accept? Say, if we will accept 70 reservations, and there is a high chance that some 50 will show up, and then some 10 persons will stand and watch the performance standing. So he didn't want that, and he wanted to limit this risk to 5%. So we need to calculate the maximum number of reservations he can accept. Okay. So first, let's prepare, then solve by R. So using R. So let n be that number of observations. Not observations, but sorry, reservations. What? Observations. Reservations. Number of reservations. Okay. So n is something larger than 40. X is the number of persons that will come, that will show up. Okay, among that n. So n persons made reservations and X will show up. So the problem is the following. The club manager wants to have that the probability that X will be larger than 40. So what this means, this is the probability that more than 40 persons will show up and someone will stand, look at the performance, watch the performance standing. So he wants to have this 0.05, 5%. Sorry. Okay, so we need to find that maximum n for this. Okay, and now we need to consider the distribution, think about the distribution of X, the number of persons that will show up. Here, of course, we need to do some assumptions. The assumption is that the probability that, not the probability, the fact that the person will come to the club or not, or decide not to go, is independent. That facts are independent for different persons. In fact, in reality, this is not the case because people are coming in pairs, in groups, and if one is not showing, maybe the other ones are not showing up. But in this case, we will assume for simplicity that the fact that persons will show up or not are independent. So if we have independence, we have n persons, n reservations, n persons with reservation. So n trials, and each person can show up with probability 0.75 and will not show up with probability 0.25. So in this case, the success is that person will show up. Person will show up. Okay. Now we need to calculate the number of persons that will show up among the n reservers. So that is given by X, and in this case, because we are doing n repetitions of a trial. One trial is one person, choosing one person who reserved the seat in that club. So we are doing binomial experiment with n persons, and the probability of success, the probability of person showing up is 0.75. Now we have the distribution x of x, binomial distribution, and we want to calculate this probability that x will be larger than 4t. Okay, and we will find the largest number n such that this probability is less or equal than 0.05. Okay, now having this distribution binomial n 0.75, we will calculate this probability with R. So what I'm doing, I will take n to be equal to 41. Say 41 persons reserve it. What is the probability that x will be larger than 40 if here we have 41? Then I will change that n to 42, then 43, and I will calculate all these probabilities up to some number, say 70 or 50, 60 maybe. Okay, so I'm calculating these probabilities for different n's and using R. Of course, let me erase this. So go back to R. So this is my R. I'm erasing everything here. So say n is equal to 41 or 40. Let me do that 42, and then I will change to 41 to something. So n is 42. What I want to do, so I want to calculate the probability that x is larger than 40. So x is larger for 40 means I need to add the probability that x is equal to 41 or x is equal to 42. So the probability that x is equal to 41 is the same as d binom. So this is the probability, PMF value at 41. When size is the number of trials is equal to, so number of trials is n, n persons reserve it, and probability of success of showing up is 0.75. So this alone will give what is the probability that 41 persons among 42 reservers will show up. The probability is very small. Okay, then if I will change this to 42, then this will give what is the probability that all persons among that 42 will show up, and that is small again, 10 to the 6th order. Okay, now I need to add that probabilities because I wanted to calculate the probability that more than 40 persons will show up. So adding that probability I can do in the following way. So I am writing here 41 to 42. This is a vector consisting of 41, this is a vector consisting of coordinates 41 and 42. Let me run that here, say 41 to 42. If I will run this, that will give 41 and 42. Okay, so I'm calculating the value of my PMF at 41 and 42. So this will give a vector. So I'm running that. This is giving the same probabilities but as a vector. And I am summing the elements of that vector. If I will write the sum, so this is a sum, that will give the sum of that probabilities, that elements of vector. Now I want to see if this sum is less or equal than 0.5. So in fact, the sum is giving the probability of having more than 40 persons. Okay, this was for 42, but let's do that for all elements. So I'm writing a for loop. So for loop is in R is in this form. So for n from 41 to say 60, do the following. Okay, I want to cut this and put it here. Okay, so calculate this. So let me denote this by P. Calculate this, but I need to calculate that for a vector starting from 41 to n. So what I'm doing, I'm calculating for n, which can be say 50, for n 50. I need to calculate the probability that I will have more than 40 persons. That is, I need to calculate for 41, 42, up to 50, and then sum that probabilities. And then I want to do the following after calculating. So print, cat is for printing. So print the following. So n is equal to, and then print n. Then print some space. Then maybe I can put a comma here. Then print probability. Probability is equal to, and then print that P, and then print new line. And new line is given by this symbol. Okay, now I can run this. Hopefully it will be okay. Yeah, I have the result. So now, yeah, this is for 41. If I have 41 reservers, 41 persons that have reserved it, then the probability that more than 40 persons will show up is this much. It is very small. If for n42 is this much, and we can see that, yeah, this is that breakpoint where the probability is less than 0.05. After this, if 48 persons will reserve, then the probability that 40 will more than 40 will show up will be higher than 5%. So maximum number is 47. He can accept 47 reservations, and the risk will be less than 5% that more than 40 persons will show up. Okay. The last distribution I wanted to cover today is the geometric distribution. This is very much connected with Bernoulli distribution. So I want to give first the definition, then interpretation. Definition is the following. So distribution name is geom. P is a probability parameter of that distribution. P is not 0, P is from 0 to 1. And we will say that X has a geometric distribution with that parameter P or probability P, and we will write like this. We'll write like this. So this means that we are reading this. X is a geometric random variable with probability P, or X is distributed as geom P. If its PMF is given by this formula. So the probability that X is taking the value X is a natural number, is P times 1 minus P to the X minus 1. I will explain this soon. So in the table form, the PMF is the following. The probability that X is 1 is P. The probability that X is 2 is P times 1 minus P. The probability that X is taking the value 3 is P times 1 minus P squared. The probability that X is K is P times 1 minus P to the K minus 1. So what is showing this? Assume we have a simple experiment with success probability. P is the probability of success. So what is showing this capital X, our random variable? Our random variable is showing how many trials we need to do until having the first success. So until first success, how many trials we need to do. X is 1 means that the first was success, and the probability that the first was success is P. That the first experiment resulted in success is P. Okay, X is 2. What it means that X is equal to 2. X is equal to 2 means that the first one was failure, and this is the probability of that failure. Then the second trial was success. So what it means that X is equal to 3. X is 3 means that the third one was the first success. So the first one was failure, then the second one was failure, then success. And because we are doing, I forgot to say that we are doing independent trials up to having the first success. Because of independence, we need to multiply the probabilities. The probabilities of failure is 1 minus P, 1 minus P, and P. Okay, so what this means, X is equal to K means that we had failures K minus 1 times. So this is K minus 1 times, K minus 1 times. And then the last trial was success. So we have K minus 1 times 1 minus P and times P for success, etc. So the range of this random variable is infinite, in fact, but countably many infinite. And these probabilities sum up to 1, and I'm asking you to prove that the sum of these probabilities will give 1. You need to use geometric series sum formula. And the other exercise is to calculate the CDF and graph the CDF of this random variable, geometric P, for some value of P. So take P equal to, say, 0.5 and calculate and draw the CDF of that random variable X. Okay, so interpretation usage. Geometric distribution gives the model for counting the number of repeated trials until the first success. So if X is geometric P, then we are doing independent repetition of some simple experiment. So we have simple experiment, we are repeating that. In each simple experiment we have an event, the happening of which is success for us, and the probability of that success is P. And X is showing how many trials we need to do until the first success will be shown. In other words, geometric random variable is the discrete waiting time for the success. So there is a term waiting time in probability. So this is geometric random variable is a discrete waiting time until having the first success. Okay. So one note, because there are two different definitions of geometric distribution of geometric random variable. This was our definition. So our definition is the number of trials we have until the first success, including that last number of success, that's trial of success. So X is taking 1, 2, 3, etc. up to plus infinity, these values. X is 1 means the first trial was success. X is 2 means that the first one was failure, the second one was success, etc. But in some books you will find the following definition of geometric distribution. So X is taking values 0, 1, 2, etc. k with the same probabilities. And in this case, X is not the number of trials up to having success, but X is showing the number failures before the first success. So in this case, if people are writing in this way our geometric distribution, then it means that X is the number of failures before having the first success. So X is 0 means 0 failures and the first one was success. So X is 1 means 1 failure before the first success. So success was the second trial, etc. So we will use this definition, of course. By the way, let me show the Wikipedia page. So this is Wikipedia page for that geometric distribution, and you can see two definitions here. One is with values 1, 2, 3. The other one is with values 0, 1, 2, 3, etc. The failures, number of failures before the first success for this case, and number of trials needed to get one success. And here you will see that support that PMF for different cases, when case running from 1 to infinity and case running 0, 1, 2, up to infinity. Okay, let's move back to our lecture slides and give some examples. We are rolling the dice several times until first time we will get 5 shown. So P is the probability to get 5 in one roll. And we know that for a fair die, the probability of having 5 is 1/6. So we are repeating, rolling that die until we will have 5. Let X be the number of rolls that we will do up to having 5 first time. Then X is geometric with probability 1/6. And this means that, what this means? This means that X has the following PMF. So it can take the value 1 with probability 1/6. So the first one was success. The second trial was success. And the previous one, the first one, was failure. So one failure probability is 5/6 times the success probability 1/6. X can take the value 3. So two failures with this probability, and the third one is success. For 4, we will have 5/6 cubed times 1/6, etc. So up to infinity. So this is the short notation for this PMF. Okay. Another example of the geometric distribution concerning geometric distribution is the following. So assume a couple wants to calculate the number of children they will have until the first boy. Assume that we know that the probability of having a boy is this much. And suppose that having a boy or girl is independent of the previous children. So we need to use that independence to have the geometric distribution. Okay, let X be the number of children they will have until the first boy. So X is 1 means that the first child was a boy. X3 means that the first 2 children were girls and the third one was boy, etc. So X is showing the number of children until having the first boy. Having a boy is our success in this case, success probability 0.49. So X is geometric with probability 0.49. And this is giving the idea, completely describing the PMF of X. And we can calculate probabilities concerning that X using the PMF. Let's move forward. So assume we are asking randomly AUA students until we will find the first 4 GPA student. The number of students we will ask until meeting that first 4 GPA student is geometric. So if X is that number of students we will ask until meeting the first 4 GPA student is geometric with probability P, And probability P is the probability of AUA student to be a 4 GPA student. So the ratio of 4 GPA students to all AUA students. Well, this P is calculated by using statistics. This is the way to calculating that using statistics. Okay, and you can give a lot of examples of this type. Now some problems to solve concerning the geometric probability. Assume X is geometric with parameter 0.8, with probability 0.8. So calculate the probability that X will be larger than 2. So what this means, I'm reading this in the following way. So X is a random variable with the following PMF. X is taking the value 1 with probability 0.8. X is taking the value 2 with probability, well, 1 failure and 1 success. X is taking the value 3 with probability 2 failures and 1 success. 4, so 3 failures and 1 success, etc. So etc, etc. Okay, so the first part is asking to calculate what is the probability that X will take values larger than 2, either 3 or 4 or larger. Okay, so it is much easier to calculate again by using that complement formula, complement probability formula. So this is the probability that X will take values less or equal than 2. This is 1 minus the probability that X will be 1 or 2. So we have two cases when X is less or equal than 2. The probability of the first one is 0.8. 0.8. Let me use this kind of thing. And then the probability that X will be 2 is 0.2 times 0.8. So this will give the probability that X will be larger than 2. And what is the probability that X will be between 4 and 8? So the probability that X is between 4 and 8, 4 and 8 is the same as the probability that X is equal to 5 or is equal to, probability that X is equal to 6 or probability that X is equal to 7. Well, I'm not reading correctly. I need to say the probability that X is 5 or X is 6 or X is 7. And this is the probability of X being 5 plus the probability that X is 6 plus the probability that X is 7. And now we can add these numbers. The probability that X is 5 is 0.2, the probability of failure, 4 times failures, and then success, here 5 times failures, success, and the 6th one was success, and 6 times failures, and the 6th one was success. So we need to add these 3 numbers to get the probability. Okay, let's move forward. 2 persons, A and B, are playing the following game many times. They are repeating, playing. Every time B is keeping in mind an integer from 1 to 10, including 1 and 10, and A tries to guess that number. We assume that we have independence in games. What is the probability that A will give the first correct guess in less than 20 plays? So we'll give the first correct guess. So let's model this. How to model this problem? So let's success is giving correct answer. So this is our success. Probability of success is the p, the small p. The probability of success is probability of guessing correctly, and the probability of guessing correctly is 1/10. We're assuming that guessing each number is equiprobable. So one is keeping in mind numbers from 1 to 10, and the other is guessing. The probability of having the correct answer is 1/10. Okay, so what is one trial? One trial is when B is keeping 1 times in mind a number and A tries to guess, is giving either correct or not correct answer. Okay, so we are repeating this up to having the first correct guess. So if X is the number of games until the first correct guess, or which is the same, the first success guess. Sorry. Then, of course, X is geometric with probability of success 1/10. So this is that important part. So we have modeled our problem by using our well-known geometric probability. So the number of games until the first correct guess is geometric with probability of 1/10. Now the problem is asking, calculate the probability that it will give the first correct guess in less than 20 place. So calculate the probability that X is less than 20. And this can be calculated in the following way. So X is less than 20 means either X is equal to, so I'm writing in the sum form, probability that X is equal to K, and K is running from, because the values of X can be either 1, 2, 3, so we are starting from 1 to including 19. Okay, and now if I will try to continue from this point, let me erase that this part. So I'm erasing this and continuing from this point, from this part. Okay, so I need to add, K is running from 1 to 19. The probability that X is taking the value K means K minus 1 times failure. So 1 minus 1/10. So that person A is failing K minus 1 times. So K minus 1 times. And then giving correct answer. Of course, you can take this out and calculate this by using geometric series formula, geometric progression sum formula. Sorry. Okay, I will not calculate this. You can do that by yourself. Okay, so geometric distribution and R. Let me draw the geometric distribution PMF and do some sampling from that distribution using R. So this is our R. I will delete this. Sorry. Okay, deleting this. Now geometric. If I will write, I want to first generate random numbers. Do that experiment for geometric random variables. Our geom, the name is geom. Here I need to write two parameters, n and probability. How many experiments I want to do? Just one experiment. Probability is equal to, say, 0.4. what will do this command. So I'm doing behind this, or computer is doing an experiment many times. The probability of success in that experiment is 0.4, and computer is calculating how many trials it needs to do to have the first success. So if I will run, I'm running this, I'm getting 0. So in fact, R is using the other definition of that geometric random variable, the number of failures. So 0 failures, the first one was success. I'm doing that again, 0. Sorry, let me do that experiment again, 2. What this 2 means? 2 means that 2 failures before the first success. So the first trial was failure, the second one was failure, and the third one was success. I'm doing that again, 1. So just the 1 failure before the success. 0, 2, 2, 6. So 6 means that first 6 was failures and the 7th one was success. Okay, so let me do, say, 12 experiment of that type with probability 0.6. So I'm running this. I have 12 numbers. So 0 means the first one was success. Another try. The first one was success. Another try. The first 2 were failures and the third one was success. First is success. First is success. First is success. 2 failures, then third one was success, etc. So it is doing 12 times geometric trials. So repeating, doing trials up to the first success and showing us the number of failures before the first success. Okay. Now I want to draw the, like this, I want to draw the PMF graph. In fact, PMF will be defined for every natural number, but we cannot draw for any natural number. We will just limit up to some point. So say x is running from 1 to from 0, because this is in our geometric random variable is showing number of failures from 0 to say 15. So I'm running this. Y is the dgeom. I want to have PMF at that points at 0, at 1, at 2, at 15. For here probability is say 0.6. I'm doing the same. So I'm running this also and plotting that points xy with horizontal lines. Type is equal to h, and then adding that points. Sorry, I forgot to change back to one graph show. So parameter mf row is equal to, I just want to have one row and one column. So I'm running this and then running this again. Okay, just one picture in graphical window. Then I want to add points x, y with point character, say 16. Well, something is wrong. Points, yeah, I forgot to write s. Okay. So this is the graph of our PMF for geometric random variable with probability 0.6. Now I want to draw the CDF. CDF is calculated with pgeom. So because it is a function defined for any real number, not only at integers or things like that. So I need to have a running variable. So t is running from sequence from -1 to say 7 with step size 0.01. So I'm running this, then calculating z is equal to pgeom, the value of CDF at that t, with here I need to write the probability. Probability is 0.6, geometric distribution with parameter 0.6. I'm running this and then plot t z type is equal to, well, let me write L first, or let me just skip this maybe, and you will see the result. Okay, what will give this? So this kind of things. At every point it is doing a small circle. So if I will add type is equal to line, well, this will give something like this. This is already okay, but there is a parameter s step, something like this. Okay, this is the CDF graph of our geometric random variable. By the way, in reality, we do not have these horizontal lines. We have just jumps here. At the point 0, the value is this much. At the point 2, the value is this much, because we have that CDF is right continuous at every point. Okay. So let's move back to our slides. We have few examples. Now plot and compare PMFs of two geometric random variables with different probabilities. Say compare geometric with 0.4, the PMF of this and of that. So let me do that in R again. So PMFs, I have the first PMF. I want to have the other one. So I'm copying this, passing it here, changing to say y1. Probability is 0.3. Here I need to have y1, and I want to change the color. Color is say red here, or green maybe. And points, again, I want to have that points again in green. Color is equal to green. I need to adjust the values. I know that, well, let me show that. First, I need to run this tree. I'm selecting them, hitting Alt-Enter. That is showing the graph of the first PMF. Then I'm keeping this graph, new is equal to true. Then I'm drawing this. Okay, you can see that there is a mess here. Some values are overlapped and showing different numbers in different places, or same numbers maybe in different places. To avoid that kind of problems in my plot, I am choosing ylim, the limits for y to show. So start from 0 to show me from 0 to, let me choose 0. Because the first probability will be 0.76, sorry, I can take 0.7 here. Okay, and I'm doing the same. I'm asking to plot the second one, sorry. I need to copy this, Control C, not here, but here, Control V, yeah. Now I can do the plot and have this kind of picture. So black one is for probability 0.6 and red one, not red one, but green one is for probability 0.3. So you can see that we have this decreasing type of probabilities. So the probability that we will have 0 successes, so the first one will be not 0 successes, sorry. The probability that we will have 0 failures before the first success for the geometric with 0.6 is exactly 0.6. So we have around 22% probability that we will have 1 failure before the first success, etc. So you can see that this probability is very high, but it is decreasing very rapidly. But for geometric with probability 0.3, we have the green version. The probabilities are decreasing more slowly. Okay, so we are moving back to our slides. And an important property for geometric distribution is its memoryless or forgetfulness property. So let me give that property, state that property. Assume that X is geometric random variable with probability P, geometric P random variable. For any number n, natural number, the probability that X is larger than n is 1 minus P to the n. So this is not that memoryless property. These two are memoryless property, and more frequently this is called the memoryless property. Okay, let's talk about the second property. The property is the following. If X is the geometric P random variable, then the probability that X is equal to m plus n, given that X is larger than n, is exactly equal to the probability that X is equal to m. So if we know that we have made more than n trials until the first success, and we are calculating what is the probability that we will do another m trials. This is the same as the probability of having the first success in the nth trial. Okay, and I will give again this interpretation of memoryless property soon. I want to prove this because we have very easy calculations for that. And the next property, that memoryless property, is the following. The probability that X will be, the first success will be on the step that is larger than m plus n, given that we have waited already n steps, that X is larger than n, is equal to the probability of X is larger than m, this m. Okay, so let me prove this. Let me erase, move to blackboard. So what I have, X is geometric with probability P. What this means? This means that the probability that X is equal to K is equal to, so K minus 1 times failure, K minus 1 times failure, and the kth one is a success. So this is what this means. Okay, so we want to calculate the probability that X will be larger than n. So this is equal to the sum of the following probabilities. Because we have disjoint, we will have disjoint events. So X is equal to K. K is running from n plus 1 to infinity. So if x is larger than n, then x is either n plus 1 or n plus 2 or n plus 3, etc. up to plus infinity. So this is equal to the following. So probability that x is equal to n plus 1. This is p times 1 minus p to n. Plus the probability that x is equal to n plus 2. This is p times 1 minus p to n plus 1. Plus the next one will be probability that x is equal to n plus 3, and that is equal to p times 1 minus p to n plus 2, plus etc. up to infinity. If we will take out that factor p, we will have 1 minus p, or let me take out that 1 minus p to the n2. We can take that factor out also, 1 minus p to the n, and we will be left with, here I will have 1, plus here I will be left with 1 minus p. In the next term I will have 1 minus p squared, plus etc. So here I have a geometric sum, and I can calculate it easily by using the following formula. So the first term, which is 1 over 1 minus the ratio of sequential terms, consecutive terms. So the ratio is 1 minus p. Okay, and this will give 1 minus p is giving p. We will cancel this p with that, and we will be left with 1 minus p to the n. Okay, this was the calculation of this probability that x is larger than n. This is the first part of that property. Let's move back. So we have proved this. Now I want to prove this. Let me do that on the board. So I'm erasing and going to the board. So probability that x is equal to n plus m given that x is larger than n. So by definition of this conditional probability, we need to calculate the probability that x is equal to n plus m. Let me recall that n and m are natural numbers, and x is larger than n, over the probability that x is larger than n. And this is equal to the following. So x is n plus m and x is n. We can just write the probability that x is n plus m, because this n plus m will be larger than n, and over the probability that x is larger than n. So because x is geometric with probability p, this is the value of PMF at n plus m. So this will give p times n, p times 1 minus p to n plus m plus, not plus 1, but minus 1. And over, we have calculated this, and this was 1 minus p to the n. We just calculated in the first part of that property. So if we will cancel this with that n, we will be left with p 1 minus p to m minus 1. And this is exactly the value of our PMF at the point M. So this is the probability that X will take the value M. Okay, and sorry, I'm leaving the proof of this property, this memoryless property of geometric random variable geometric distribution, to you because it is very similar to this. Okay, an example of that memoryless property. Assume that the probability that a customer will buy suriki lavash is 0.005. Then the following probabilities are equal. So the fifth customer will buy suriki lavash, or the 15th customer will buy suriki lavash, given that the first 10 customers have not bought that suriki lavash. So that 10 customers that have not bought suriki lavash are not so important. So we are starting again, and having this and having that is the same. This is that memoryless property for geometric random variable. And another important remark, one important remark is that only discrete random variable with memoryless property is the geometric random variable. And mathematically is the following. Mathematically, the following holds if X is a discrete random variable with this range, consisting of all natural numbers, and if X is satisfying this property, memoryless property, for any n and m, then there exists a P, number P, such that X is geometric with P. And later we will learn that the only memoryless but continuous random variable is the exponential one. Okay. So the next one is Poisson distribution, and we will talk about Poisson distribution in our next lecture. So thank you. Bye. Until the next lecture.